10 to the minus 6 to 10 to the 6. But now if my data set size has to come into that, now I have to scale that by the number of data points or something like that. And that just seems sort of not right. Does that make sense?
Yeah, thanks.
Great. Are there any other questions?
There was a question in the chat about how long students will have for the following homework. So, you know, we're aiming for approximately 2 weeks for every homework, plus or minus a few days. I think that's like our, right, and homework 2 is due tomorrow. Just a reminder in case anyone has forgotten that. So the homework 3 will come out shortly thereafter, maybe Wednesday or Thursday.
Wait, sorry, can we go back to the question that the guy just asked? I'm not sure I quite understand why we have to scale the regularizer.
You don't need to. It's just, I'm saying it's convenient so that like it'd be inconvenient if lambda had like an n built into it. So I'm just saying, like, when I do a hyperparameter search, regardless of the size of my data set, I will try to do a hyperparameter search for this lambda from like 10 to the minus 6 to 10 to the 6. That's the range that I'll consider.
Mm-hmm.
But now, if your lambda, that's relative to a loss function that's normalized. So I'm not. It's the average of the losses instead of the sum of the losses.
So it might be helpful to think about this. Like, I think we talked about what the SGD step looks like, right? And the SGD steps look like something that has some function of the regularizer in it, right? And if you want, you know, as I recall, right, I'm just vaguely remembering what the slide looked like, you know, there was some, you know, we think about the loss function broken up into different terms for each of the individual data points. And if we do that, we also think about like an additional component of that loss per data point as having some fraction of the regularizer incorporated into it when we take that gradient step. So, you know, if you think about the loss broken down into portions for each of the different data points, you sort of divide the regularizer into each of those, right? And that might, maybe that viewpoint will be helpful.
Okay, I'll look into that. Thank you.
Okay.
Yeah, it's not a necessary thing, it's just a convenient thing for practice. Okay, so again, we're gonna wrap up some supervised learning, some basic concepts of supervised learning before moving on to unsupervised learning. So one of the simplest possible classifiers we can talk about in like estimation methods is nearest neighbor. And a lot of times we'll like actually start with this model when we start machine learning. But sometimes it's more convenient to talk about linear first. So recall the conversation that Jamie had when she introduced classification and the notion of something called the optimal Bayes classifier. And basically this classifier, it's sort of the all-knowing classifier. And basically it predicts 1 when the probability of y is equal to 1 given a particular x location is greater than 1/2. And it predicts -1 when the probability of y is equal to 1 is less than 1/2 at a particular value of x. And then so if on the left-hand side, we plot some data down where we have positively and negatively labeled data, where the orange is positive labels, blue is negative labels, then the Bayes classifier is this Bayes decision boundary is this black line, and the sort of checkered colored there, or hashed color there is where you predict positive, where you predict negative. So this is the best thing you could possibly do. This is in really the only sense optimal in terms of classification error. Of course, we can't do this because we need to build a model. We don't have the probability of y is equal to 1 given x equal to x. If we did, then we would just do this, but we need to learn a model from data. And so the model we looked at, so far in this class basically has been linear models and then glorified extensions of this, like neural networks and kernel methods, which are basically just compositions of linear functions or projecting to a higher dimensional space and doing a linear function there. And what we can see here is that when we fit a linear function to this, we get a pretty different looking boundary than the Bayes classifier. Meaning the Bayes classifier looks very, very wiggly. It's sort of making its way around all the data. It seems like it's doing a pretty good job, making very few misclassifications. But then when we look at the linear classification, it looks like we're really screwing up on some data. Like these points here should clearly be labeled as +1, but they're just being screwed up, and same thing for here. And so a more natural, what we'd really like to do is, like, when I say that, when I'm circling these points, like, oh, you know, these ones here should really be labeled positively. Because, like, look, I mean, all their like all the close points together are all labeled the same label. That's probably not a statistical fluke. It really is -1. And then same thing for these guys here. It's just sort of intuitively, I'm looking at these and predicting that, like, well, they're all the same label. They're averaging out sort of locally. So that really should be positive or negative based on the local neighborhood. And so K nearest neighbor is captures this concept exactly, where basically what it does is, this is a different kind of model. And at each point X, it will look at, for 15, for 15 K nearest neighbors. So we will look at, for every point X, we'll look at the 15 nearest points in, say, Euclidean distance, and then just do a majority vote of those labels. And if we do that, we get this decision boundary that looks very curvy. It looks to be following the data very well. There's no sort of obvious place where it's getting the wrong answer. I mean, maybe here, but on the whole, this looks like a much, much better classifier than our linear boundary. And if we return back to the Bayes classifier, it's basically matching what the Bayes classifier is doing. If you sort of squint at it, it's doing a really, really great job. And so this is the 15 nearest neighbor, and you can get even more specific. It might, you know, it's still missing this this piece here. Maybe, and what you can do is, you know, with the 1 nearest neighbor, get to, you know, smaller number of neighbors, and then, oh, now we've captured that. We've captured this cluster over here that we missed before. But one thing, you know, but we're also picking up a lot of spurious noise in these other regions. So this 1 nearest neighbor classifier is really just looking at the nearest possible point and classifying every location that's similar to the most nearest point as whatever label that is. And so, like, you can see this trend that as when the number of neighbors is very large, it's a very smooth decision boundary. With an extreme, if I took the number of neighbors to, like, the maximum size of the data set, you just predict the same label for every location, right? And so that would be the simplest classifier that have very, very low bias. Sorry, very, very low variance, but extreme amount of bias, because it would just be classifying everything as the same label, which is clearly going to be wrong. Whereas 1 nearest neighbor classifier is the alternative, where basically it's going to have extremely high variance, because with different draws of the data, I might see completely different decision boundaries. But the bias is extremely low of this classifier. The bias is low because on average, this is really going to learn whatever data comes to it. And so the expected sort of label at any particular point, if you think about it, the expected label is basically the truth. At any particular point, like, what's the probability of getting the right label? Well, it's basically dependent on how close that nearest neighbor is. Because if that nearest neighbor is right on that point, you know, then you're basically, that is an unbiased estimate of what the label should be at that point. And so this is sort of this beautiful sort of trade-off between bias and variance. Because if we have these plots that we've been seeing before, where when we go from left to right, complexity starts off very small and then gets larger. Now we sort of have this sort of interesting behavior where, like we said, if the number of neighbors is very, very large, like 150, then the complexity is actually very low for nearest neighbors. right? Because the amount of boundaries that you can have, if you're averaging 150, you're taking the majority of about 150 labels, it's just going to be a very, very slowly moving decision boundary. Whereas if you look at one nearest neighbor, it's going to have an enormous amount of flexibility and a very, very high variance. And so what we start off with is this classifier starts off with very low variance and high bias on the left-hand side, and ends with very low bias and high variance on the right-hand side. And then so, of course, there's going to be some sort of middle here where you get the sweet spot and you get the Bayes optimal, or you get the best classifier on this particular data set. A few plots here. So this purple line is the Bayes classifier. This is the best error that would have been achievable by the Bayes classifier. And we can see that the one near, or the, I guess this is 11 nearest neighbors, is about getting the best possible. It's almost as good as the Bayes classifier. And for reference, we've put the linear up here, which is equivalent to about 69 nearest neighbors, at least in terms of this error. And as we see, as the number of neighbors decreases, the training error will go to 0 because you're getting more and more complex. The more complex the classifier is, the more you can fit any training data and overfit that training data. So we expect the training error to go to 0, but we get this characteristic test error curve where it goes down and then it goes up again.
And I'll just jump in for one brief moment and mention that the y-axis here is labeled test error. It might be better to label it error since we have train and test on the plot. I was confused myself, so small thing.
You do true error because we actually have this data set. And so so as k goes out to infinity, the bias increases, the variance decreases. As k goes to 1, the bias decreases, but the variance significantly increases. So nearest neighbors are awesome. They're really simple. They have like this beautiful sort of bias variance trade-off property and story. They seem to be doing very well, at least empirically here on this particular example. It seems a very flexible boundary. It seems to be getting very close to the Bayes classifier, much better than linear. And they're very flexible. You can use different distance metrics. So this is the L infinity norm. This is the L1 norm. This is the L2 norm. And then you could have some shaped norm like this for some matrix A, where you're weighting different dimensions different ways. You can even have kernelized norms. So like what you could do is you can, because you can write x2 squared as equal to just, because you can write x minus y 2 squared as equal to x transpose x minus 2x transpose y plus y transpose y, well, that's just a bunch of inner products. So then I can just write this as terms of kernels as well. And so this is just k of xx minus 2k of xy plus k of yy. And one reason why you'd want to do this is if you're wanting to project to high dimensions, and maybe you think the function's better there than in the original space, or maybe you only have a similarity function defined between 2 data points and not you don't even have a feature space. It's another reason why you use kernels, is because there is no natural d-dimensional feature space to do your learning in, but you can sort of define a similarity between any 2 points. So that's one way you like to do this. If you did L2, which is by far the most similar and most popular and sort of obvious sort of distance function that you'd use, then you get these nice sort of Voronoi regions is what we like to call it, or what they're called, where basically everything within this region is labeled as the same classifier. And these are just sort of neat to think about like how these would be classified. Just pretty pictures. And moreover, just okay, the classifiers are very intuitive, they're very simple to implement, they're very nice, but they also have extremely strong theory and guarantees. What it says is that, so suppose we have the situation where I get some data set, the standard setup, where we have xi and rd and yi and 0, 1. And we're getting these IID draws from pxy, okay? And so we're in the standard machine learning setup. And then what this theorem says is that suppose that px is supported everywhere in rd, or analogously, if x has finite support like in 0, 1 to the d, so it's just some hypercube, that's fine too. I just need to have that the density of x doesn't have holes in it. It's sort of like connected. And it's sort of, there's no like discrete points that it can be at. And so it's just saying that px is smooth. The distribution of p of x is smooth. And we also need that probability, the regression function, that probability y is equal to 1, given x is equal to x, is also smooth. And so all this is saying is that, like, if you had x as being, say, distributed from a Gaussian, and then y is just some regression function that's sort of slowly varying and continuous, then this would be satisfied, no problem there. And then, so under these, pretty benign assumptions, it says that as the number of data points goes out to infinity, the one nearest neighbor classification rule has at most twice the Bayes error rate. Okay, so if the Bayes error rate is 0, what this is saying is that as n goes out to infinity, you are learning the optimal rule as n goes out to infinity. Or if the Bayes error rate happens to be 0.2, then you're learning something that's 0.4, which is not so great. But this kind of result is actually quite strong, because it's a non-parametric guarantee, is making no assumptions about like what parametric sort of form p of y is equal to 1 given x looks like. It's just extremely general. And I'm not going to prove this. I did leave a sketch here if you wanted to go through it on your own. It's a very, very simple proof. And you can generalize to k classes very easily. And so I encourage you to do that. But it basically has to do with the fact that at any particular point that you want to classify, as n goes out to infinity, there will be a data point right next to you. And because it's a data point right next to you, if I use that to classify myself, then that's basically an unbiased estimate of the true error. And then you're just talking about basically what's the probability of that bit flip happening. And it's exactly the Bayes error rate at that point. And so that's where the proof comes from. And so this seems like a pretty great deal. Very simple to use, some pretty strong theory, relative to the Bayes error rate. Why don't we use nearest neighbor classifiers everywhere? Nearest neighbors are pretty rarely used in practice. And the reason why is what I'll get to in a moment. But before I do that, we could. Oh, sorry. Okay, so sorry, I just got a phone call. So if we're doing, in addition to just classification, we have nice classification guarantees. We also have regret. You can always do regret with nearest neighbors as well, in a very simple way. Basically, you just take the k nearest neighbors at any particular point, you average the k nearest neighbors and take that as your function, as your estimator. Pretty simple.
So there are a couple questions in the chat that might be good to answer. So one of the questions is asking about the complexity for k nearest neighbor and whether it's influenced by the value of k.
Yeah, so that is this plot here. So if I have one nearest neighbor, that's the most complex, because one nearest neighbor is going to fit every little nook and cranny of this data that you see. And it will always have the most complex decision boundary, and can learn sort of anything. The space of decision boundaries are just like very, 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 very large. Whereas if I increase the number of neighbors, now if I'm doing 15 nearest neighbors, the amount of sort of variation is going to be significantly limited, because I need to just the rate at which the classification label changes when you're averaging the 15 nearest neighbors really goes down. And so the complexity, as the number of neighbors goes up, the complexity goes down. And so that's why we like to look at plots like this, where we're starting with low complexity to high complexity. And it's sort of the inverse relationship to the number of neighbors.
And I guess yeah, that was something you'd already covered, but for whatever reason, I interpreted that as like computational complexity. And,
oh no.
Right. No, not your plot, but the question. But I'm not sure that that's what they were asking. Anyway, go ahead.
Computational complexity. Yeah, I mean, that's a good question. It's annoying because every time you need to classify a point, you need to look at your entire data set in theory, or like with a naive implementation. So like if your data set is very large, that can be a very intensive search. But in practice, you could do things like very, very intelligent data structures like K-ball trees and KD trees and things like this that make it not too bad. This is not really the real reason why people don't use nearest neighbors. We'll get to the real reason. But there's still an extremely important class of functions to look at, and we'll see when they are applicable. So you can do things like regression with them, and just average the things. But you might also say like, well, maybe I don't want to look at the k nearest neighbors. Maybe I want to do some sort of weighted function. So I want to define some kernel function where, you know, nearer neighbors are given a larger weight, farther away neighbors are given a smaller weight. You can compute this over the entire data set, and then you can do a weighted average of all the labels. That's totally fine too. You can do this on all n data points, or just like the top 50 neighbors, you know, to your heart's delight, any of these kind of extensions. And so this typically gives a smoother sort of boundary. If you look at this regression function, the green on the left, it's very crunchy, whereas on the right, it's very smooth. It's very characteristic of these kind of smoothing methods. And you could also wonder like, well, if I'm just doing a weighted average of these yi's, I could do something even more intelligent. I could just look at my 15 nearest neighbors and then do local linear regression on just the 15 nearest neighbors. Totally reasonable thing to do. That's called local linear regression, and that works very well. A little bit better than just a straight up average, especially if you have functions that tend to vary quite a bit. So these are all things you can do. They're all variants of nearest neighbor. If you know the inevitable answer to the question, can I do X? The answer is yes. It's very reasonable, and you can try things out. So why don't we use nearest neighbors a lot in practice? One of the reasons is the curse of dimensionality. And what this is basically saying is that things in high dimensions are not acting as they do in lower dimensions, or your intuition for lower dimensions and local neighborhoods isn't really accurate. So this first example, what people like to talk about is like, if you have this unit hypercube in 0, 1 into the D in D dimensions, so it's just you know, the hypercube in D dimensions. And the question is, if I have a neighborhood with one of the corners at the origin 0, 0, 0, and then the other far corner at R, R, R for some little number R between 0 and 1, the question is, how big does R need to be before I am, you know, covering say 0.1 of the volume of this hypersphere or hypercube? Because like in one dimension, of course, this is really simple, right? If I have just one dimension, then if I want to cover a volume R or 0.1 of one dimension, I just need R to be 0.1. If I want the volume to do R2, then it's a little more complicated. I need to have something that's a little bigger than R for exactly the right equation, but it's something. But the point here is that we've got these plots already calculated for you. And so if we look at just this line here, this is covering 0.1% or just 10% of full hypercube. And what it's saying is that in 10 dimensions, if you're in 10 dimensions, the side length, how big does R, this local neighborhood of the side length of this cube, how big does that need to be before you're covering 10% of the mass of this full hypercube? Is something like 0.8. Okay, so think about that for a moment. We want to cover just 0.1 or 10% of the full mass of the hypercube, and to do that, to cover 10% of your data, if you drew data uniform at random from 0, 1 to the d or p here, then if you wanted to cover just 10%, you would need the side length of this edge of this cube to be 0.8. And that should really start to concern you, because if the side length is 0.8, the whole point of going down this road was to look for local neighborhoods. And when the side length is 0.8, that's no longer a local neighborhood. That's basically taking up the entire 0, 1 hypercube. And so what it's saying is that in high dimensions, to find sort of points that are nearby to get the same amount of volume as the dimension increases, you need to cover a significantly larger amount of space. The notions between volume and basically like the size of some set, the local sort of radius, have some very complicated relationship and very cursed relationship. This is sort of the first example. The second example reinforces this even more. So now consider if we had data uniformly at random. So new example, get that last example out of your head. New example, data is now uniformly distributed over -1/2 to 1/2 in p dimensions. And so now it's saying, the question is, what is the median distance from a point at the origin, say 0, 0, 0, 0, to its first nearest neighbor? Okay, so what is, because on average, this data is random. And so how many, what is the distance to the one nearest neighbor if you're trying to classify it at 0, 0, 0? And in one dimension, this is, not far at all, right? This is typically pretty small, and because this is the one nearest neighbor in one dimension. In 2 dimensions, it happens to be this point here, which is a little bigger. And this is the median distance. Well, this is the empirical distance, but then we repeat this many times, look at the median. So if we calculate this though, then if we're in, say, like, if we're in 12 dimensions or 13 dimensions, the median distance, if we're in 12 dimensions, if we have just 10,000 points, the median distance is 0.5. Okay, let's like stop to think about that for a moment. 0.5 is sort of the trivial distance, because the distance to the boundary, because you're in a hypercube, and I'm saying please classify 0, 0, 0, 0, 0, the origin. But the hypercube is -1/2 to 1/2. So if the distance is more than 1/2, you're basically going to the boundary of the set. And so to say that, like, how big does n need to be to have anything non-trivial, to not being like looking at the boundary of the set, I need n to grow really, really rapidly. And the dimension really hurts you here. And so the takeaway of these two sort of examples, and I strongly encourage you to think about these on your own, draw some pictures, and really reason about these on your own. Because I think it's really hard to sort of parse this live, but it's worth thinking about. And what it's really saying is that local is not really a property that happens in high dimensions, meaning that in very, very high dimensions, everything looks very far away. The closest point, the ratio between the closest point in your data set to the farthest point in your data set is actually not that different. Everything sort of looks uniformly far away from every point. It's kind of like the universe. Like every point is pretty much as far away from every point. There is no center. And that's very much how like data looks in high dimensions, where every point, this is the plot that sort of makes this very clear that like if you don't have a substantial amount of data, meaning that you don't have data that's growing exponentially fast in the dimension, then basically what's happening is that every point just looks really, really far away. And to sort of like think about this a little more, if you wanted to have uniform coverage, if you wanted each dimension to have, say, 10 points in it, and you wanted that to be sort of like everywhere, in p dimensions, you'd really need to have 10 to the p data points. And so that's really what's kind of crappy about this, is that the curse of dimensionality is saying that in high dimensions, every point is very far away from every other point. And so if you're doing any of these local methods like nearest neighbor, the pictures that we're drawing in low dimensions totally make sense. This is a one-dimensional function. And so this notion of local makes sense. 2 dimensions looks and makes sense. These pictures make, nearest neighbor makes sense. But in 10 dimensions, every point just basically looks uniformly far from each other, because our brains can't really process 10 dimensions. But it's basically this problem that every point is very far away from every other point, because there are no local neighborhoods in high dimensions. And that's why
oh, sorry. It looks like we have a hand from Yigit.
Yeah, go ahead.
So this curse of dimensionality problem is just a problem in non-parametric models. Like, so in parametric models, as long as we have x transpose x invertible, can we say we are safe?
So this is a good question. It's a fundamental trade-off of bias and variance, because this is you're right, use the word non-parametric. Nearest neighbor methods are called non-parametric not because they don't have parameters. K is still a parameter, but they're non-parametric in the sense that their complexity increases naturally with the data set size. So as the more data I get, these methods will converge to sort of the Bayes classifier, something close to it. Meaning their complexity is basically a function of the size of the data set. And so what can happen here is that these particular methods are based on local sort of space, and they will not work very well in high dimensions. Now, you're saying, you're comparing to linear methods, they're called parametric dimension. They're parametric models. And we call them parametric because the complexity of this class is just absolutely bounded. You cannot basically, the total complexity of how many ways you can make a linear boundary, like you can cover it in a sense. I can approximate every linear boundary with a finite set of points. It is compact in a certain sense. And in that sense, we get around the curse of dimensionality, specifically because we don't need to have the number of data points grow off to infinity. This is very much, the linear decision boundary has bounded sort of capacity, its complexity capacity, and is avoiding this runaway sort of explosion of complexity. And so yes, linear boundaries or linear functions are interpolating between data in a very sort of predictable and smooth way. Linear functions are the somehow smoothest functions, meaning they're not doing something wild in between the data. It's interpolating the data in the smoothest possible way, and that is what really gets around this curse of dimensionality. It's making a bet that your data is smoothly varying between data points, which may or may not be a good idea. But so they could potentially have high bias, but typically this is an okay assumption. And that's why linear boundaries or linear functions tend to work well and avoid this curse of dimensionality.
That being said, we haven't really talked about, we've sort of treated our data set as some fixed quantity, where we have n data points in d dimensions, right? And maybe d grows. But we can also think about like d, you know, the number of features we have are often some measurements that someone's taking, right? And if you take more measurements, you can fit a higher dimensional linear model, but you'll need more data in terms of n, the number of data points you have, to give some good guarantee that you won't overfit, right? Which is, it's not a curse of dimensionality per se, but sort of as the dimension of your data set grows, if you're thinking even just about linear models, you'll need more points in your data set to be able to argue about generalization, right? So higher dimensions don't come for free pretty much anywhere.
Yeah, so like to follow up on what Jamie was saying, like to fit a linear model, if you have d features, the number of points, you need n to be about at least d. You need about d measurements, or order d, like 10 times d or 100 times d, in order to fit that model. And if you have less than that, you're probably going to overfit and not generalize very well. For nearest neighbor, you need something like n needs to be more like 2 to the d. It needs to be exponential in the dimension to be able to learn the best nearest neighbor model. And these numbers, where this is coming from, to fit, this is basically to generalize to unseen data.
And
meaning like to not overfit.
Yeah. One other intuition which might help, and I think this word was mentioned when Kevin was talking about this, is that like volumes grow exponentially in the number of dimensions, right? So like, you know, distances make sort of sense in 2D, but really what you're thinking about for a new data point in like many dimensions is like, you know, how do you have to grow the like generalization of the sphere around that data point to find another data point, right? And volumes just grow really fast, exponentially fast in the number of dimensions you're looking at.
And the connection here between volume, why we keep talking about volume, because like volume is probability. The probability of landing in some set is just a volume. It's integrating over some set of the function. So that's the connection between volume and probability, because they are the same thing.
Right. And
this is measure theory.
Sure. And if we're talking about, so far we've been talking about uniformly at random, right? Which is sort of the easiest measure we could think about with respect to volume.
Thank you.
Different norms? No, not really. Actually, by the equivalent of norms, you can look online with, actually, I think you proved this on your homework. The equivalence of norms, all norms are basically up to a scalar of each other of the dimension. So like between, I think it's like D, between like L0 or L1 norm and L infinity difference, L1 norm, it's just a difference of a factor of D. But we're talking about exponential, like 2 to the D. So like, no, any norm you use, you'll be bit by this. It's a good question though. Okay, so just to summarize nearest neighbor real quick, they're super simple, very easy to explain, intuitive, easy to implement, a little computationally intensive, but like you can use smart data structures to help with that. You can use very general kinds of distance functions and similarity functions. It doesn't even need to have any properties, just write down whatever, you know, ice cream is similar to dog in some way. I don't know. Like if you have similarity measures, you can always use nearest neighbors. This is actually a big reason why they're used too. If you can't ever have a feature representation or write down a reasonable kernel. You can use smoothing, these kernel like weighted sort of combinations of neighbors. That's totally fine. Usually smooths out the data a little bit. It does not decrease the complexity. But like the issue is that in high dimensions, data is not local. And by high, I mean like 10 dimensions, not like 1,000, like 10. And so this is why nearest neighbors are really, really strong and great for low dimensional data, like 2 or 3 or 4. But when you get to the higher dimensions, it can really hurt you. Now, one exception to this is that if your data lives on a manifold, a low dimensional manifold, meaning like, now Jamie's going to talk about this on Wednesday, but like if your data is potentially in high dimensions, but actually it's a very simple structure in that high dimension. It's almost like a string in this very high dimensional space. And in that space, that data really is kind of like one-dimensional, and then these methods will work. And so sometimes, so I don't want anyone saying that, like, Kevin, I ran on a 50-dimensional data set and nearest neighbor worked great. But basically, if that's true, then that is almost a proof that your data is low dimensional, in fact. And so, yeah. So yeah, that's all I wanted to say about nearest neighbor. They're simple, they're great in low dimensions, and high dimensions, they can really be a problem. Okay. So that basically covers supervised learning. I think in the last weeks of the course, we might also, I think we probably will cover random forest and boosting and gradient boosting trees and things like this. But for now, we wanted to get to supervised learning as fast as possible. And so we're sort of like ending the chapter on supervised learning, moving into unsupervised learning. But before ending this chapter, I wanted to return to this issue of cross-validation and validating your model, and having sort of justification for the model that you're proposing. Because if you have lots and lots of data, you can just take the average, and that average seems pretty good. Like, if you want to do cross-validation and you want to do an 80-20 split of the training and test set, that's okay. But what if you only have like 20 examples or like 15 examples? What does an 80-20 split even mean? You're going to train on 12 points and then test on 3? Like, like, you're not going to get any specificity with 3 points in your test set. And so, like, how do we do classification? Or how do we do regression and hyperparameter fitting on very, very small amounts of data? And how do we get any notion of error in this? How do we do things empirically? And then also, how do I build confidence intervals and statistics that are really complicated? So on your homework, you computed the test error of MNIST, the classification error, using Houghton's inequality. It was a B problem, I believe. And basically what you did is say, okay, these are independent random variables in 0, 1. I can compute confidence intervals on my classifier because the probability of making an error is 0 or 1, their IID. I can get some confidence interval, and I can confidently say that the classification error of my classifier is 0.75 plus or minus 0.03 with probability 1 minus delta. That's awesome. That's confidence interval. You're getting not just the error of your classifier, but your confidence in that number. How robust is that number? How real is that number? Is this question of 3/5 heads versus 30 or 50 heads? And a third sort of problem. So how do we do confidence intervals, though, for more general things, like the median of a bunch of numbers? We look at the average, right? That's what Houghton's inequality applies to, the average of n 0, 1 variables. But if I wanted you to build a confidence interval on the median, how would you do that? Or if I wanted you to find the confidence interval on the variance, so maybe you are calculating the mean squared error of some classifier or some regression function, those numbers aren't in 0, 1. They could be anything between 0 and 1,000 or whatever. How do you apply Houghton's inequality to that? Can you even? Is that going to be a tight? Sort of confidence interval? No, it's not. It's going to be really bad. How do I build confidence intervals on sort of statistics? And that's basically what the Bootstrap is designed for. And one example I really love about the Bootstrap is, you're telling me that the classification error of your entire data set is 0.75. But like, what about, this particular point? So like, yeah, over like the entire data set, it's a 0.75 error rate. But like, I have this patient in front of me, and I want to know what is the probability that this person has cancer. I don't care about the whole population that I could be seeing based on the training error and test error, or based on the data set that I saw, all the X's I saw. I care about this particular X. What is the accuracy? And we have not given you the tools to be able to do that yet. We have not been able, you can't answer this question with just cross-validation or looking at Huntington's inequality. But the Bootstrap can do this. It was invented by Efron in 1979. And Michael Jordan likes to say this is the best idea in statistics in the last 40 years, which is, kind of sad for all the PhDs in statistics. But the Bootstrap really is an amazing piece of technology. So we're going to go through it. It's also extremely used in industry a lot. People who are making decisions, they want to know not just they don't want to know just the output of a classifier. They want to know how confident you are before they start investing millions of dollars. And so the Bootstrap is one way of giving you this confidence. Okay, so abstractly, what are we doing? We have IID data, and abstractly, I'm just saying like we have data Z1, ZI. So ZI, I have a distribution F sub Z, and you can think of this as a CDF, right? This is the probability that Z is less than or equal to X. It's a probability cumulative density function. And now each one of our ZIs is drawn IID from this distribution. It's a one-dimensional distribution. And then given those n numbers, we want to compute some statistics of the data. So like the median of this data. Okay. And so that's going to get a single number out. For every one data set D, I get a single number out, which is the median of that data. But the question I'm asking now is, I want to know the distribution of that test statistic with respect to the random data set D. Okay, so I don't want you to just give me a number back theta hat. I want to know a confidence interval. I want to know the distribution of that test statistic theta hat, where T is the function taking the median or something like this. And so to do this, to simulate this process, if I knew what the distribution FZ was, what could I do? Well, what I could do is I have this one, and I could set, D1, which is drawing, Z1, ZN1, and D2, 1, 2, ZN2, and so on and so forth. I can do this sort of B times. So I get B different data sets. And if I B IID data sets according to FZ, then now I can actually just compute. I can compute theta hat of 1, theta hat of 2, theta hat of B. And now I have many, many samples of an estimator theta hat, this estimate. And then I can compute all of these guys. Then I would have some sort of distribution of theta hat I, where this is something. You'd get some distribution, and then you could say, oh, okay. So then I can build some confidence interval that includes 95% of the theta hats that this particular statistic will generate, given n IID draws from the distribution FZ. Okay, this is what I would want to do. Unfortunately, I don't know what FZ is, right? In the typical machine learning setup, we're just given n data points that are IID draws from this distribution FZ, but I don't know what FZ is. So I can't draw new fresh data sets from FZ. I have to somehow deal with this. If I don't know what FZ is, I can't draw a new data set from it. So it seems sort of stuck. I don't know what to do. And so the Bootstrap does something extremely clever. What it says, well, I know that FZ is a cumulative density function, right? So that looks like this green thing. This is the true distribution, the true cumulative distribution function of the random variable Z. But now what I have data. And so I have this data Z1 through Zn, all IID from FZ. So what I can do is I can compute the empirical CDF of this data. And you saw these on your first homework. I can just compute the empirical CDF of my NZIs. And if I compute that guy, it's this blue crunchy line. And as you might realize, or is obvious, it looks a lot like f of z, the true function. And as n gets larger and larger, this function will converge to fz at a rate of something like 1 over square root of n. And you proved this on your homework, actually. In homework 0, you showed the variance of the estimator is going down like 1 over n at any particular point. And so this is great. This is saying that I don't have fz. If I did have fz, I would just draw b new data sets, fresh draws from fz every single time. That's what I would do if I had fz. I don't have fz, but I can compute the next best thing, f hat z, from the n data points I have, and then draw data sets from that empirical thing, pretending that this empirical thing was the truth. And then, so I can do this for the first data set to get some theta hat 1, do it again, do a fresh draw again, sampling uniformly with replacement. So I'm treating f hat truly as the true fz, and just drawing endpoints from it. And then I'll compute some theta hat 2, some theta hat 3, etc., theta hat b. And then I'll have a bunch of b theta hats, these things, and then I can put a distribution, some histogram of them, and then I can look at boundaries of the 95% confidence interval. And that's what you can do. And that's exactly what the Bootstrap does. The Bootstrap, the non-parametric Bootstrap, what it does is it takes, for little b equals 1 to big B, the beat Bootstrap data set is just taking n samples with replacement from your empirical data set. So if you saw n examples, you'd draw n new points for on the B iteration, you'd sample n points uniformly at random with replacement from your data set, compute, get some data set d star b, and then you would compute data star b on that data set, and you'd get some sample. And if you repeat this big B times, you get big B sort of many of these, and then you can do statistics on these as if you're getting big B copies of the data set that you had. You don't just get one, you got big B of them. Okay, and so I think it helps to see an example. So, so in this case, if this was, if the true theta hat was this guy here, from the first data set, all these theta star B's, theta star B, you might get, some, well, it's going to give me an empirical distribution. You might get something that looks like this. You might get a lot of different, these Bootstrap samples. You're going to compute them many times. You're going to compute some histogram, and this is what the histogram will end up looking like. And so this is great because then I can do all sorts of things with it. And so, like, one often thing to do is, what if you had some, let's take a regression example. Okay, so in this left panel, I started with some data set D. Okay, I had some data set D, and I'm going to learn some kernel ridge regression on this, right? That's what I'm going to do. I have a very relatively small amount of data here. And so what I'm going to do, I start with my data set D, I perform my kernel ridge regression, and then I get some theta hat out, which is going to be, I'm calling that my function. That's just the kernel function that I learned. And that's going to be some function that goes roughly through my data. And now, so I get one theta hat. And the question is like, well, what if I want to know what the error is at this particular point? Maybe I'm predicting housing prices, and like my house lives right here, or the house I'm interested in looks right here. What is this price? I can get some prediction of it, but there was no data on that point. No data point told me what was, there was no house that looked like that particular house, but I still want to predict, what does my function estimate that housing price is, and what kind of error is on there? Is the price of the house going to be 800 grand plus or minus 100 grand, or maybe it can go up to 400 grand on the upper end, but like it's not going to go lower than 50 grand on the lower end. What is that error going to be like? So one way to answer this question is to take a bunch of Bootstrap data sets, in this case just 10 for visualization purposes, and then compute the 10 theta star b's, so a different function for each Bootstrap data set, and you'll get a bunch of these lines that look like this. So each line here is the kernel ridge regression sampled on each Bootstrap data set. And then what you can do, we can look at this point, it's about 1.2, and then we can see that, like, oh, that's the amount of variability at that point. And so then I can be pretty confident that, like, okay, well, the average is going to be something like here, but then there's this sort of this range of the theta has that I could have seen, and this is going to be a pretty valid estimate of how much this housing price is actually expected to vary, and it's better than it's pretty good. And so what you can do is you can then just take the top 2.5% and the bottom 2.5% and build these 95% confidence intervals. And you can say, and what they're saying is that, like, with probability 0.95, the point-wise sort of value of my function is going to be within these confidence levels. This is not saying everywhere is a subtle point. It's saying at a point-wise sort of way, if I look at any particular point, 95% of the time, my function will land, the true function will land within this confidence interval. And so this is one big application of Bootstrap to basically give you confidence intervals that are very non-parametric. I can ask these things about anything, and I can give you some confidence interval out. And so it's extremely powerful in this regard. And so I'll take questions in a moment. But what's super powerful about this is that it just takes, it's replicating the entire process. So if you had some classification data set, you're doing sampling without replacement to create each Bootstrap data set. You'd sample sample with replacement from your XI/YI pairs, learn some classifier, and then you do this big B times, and then you'd be able to get some sort of accuracy on basically you build confidence intervals. And the beautiful part about Bootstrap is that there is some pretty beautiful theory for it. I've very much sort of hand-waved my way around it, but basically from a theoretical standpoint, it's all asymptotic. But basically it says that these error estimates, these confidence intervals, are consistent. As n goes less to infinity, these confidence intervals are actually covering, and they're true. They will converge to the true thing under very, very benign considerations. It's very simple to use. One issue is that it can be very computationally intense. So because you're drawing, basically, instead of for B bootstraps, you're training basically B classifiers or B regression functions. And that can, if in B is typically taken to be in like 1,000 or more. So that can be pretty intense. But the idea is you would use this in situations where you had nothing else, if you need to find the confidence interval at a particular point, or if you just had very small amount of data where you only had, say, 20 examples, and then doing a Bootstrap data set is very easy, right? And this is what are you building the confidence interval on here? You're building it on the evaluation set. So you are doing a Bootstrap data set sample from your training set. The same, you have 20 points. You're going to draw a Bootstrap data set from your 20 data points. It's not going to hit every point. And so the points that you didn't hit, the ones that you didn't sample, because you're sampling with the replacement, you're going to use those as a test set. And you're going to average over this many, many times. And then that will actually give you a pretty good estimate of the true error rate. It'll give you the best thing you can do. It won't be a good estimate. It'll be the best estimate you can with so little data. And so there's a lot of great advantage to using Bootstrap. It's not the best thing, but it's extremely useful, and it gives you some amount of variability. It gives you some signal of how much the thing is varying, and that's why it's very, very useful and used so much. And yeah, but one thing as you might imagine, it doesn't work uniformly well in all test statistics. You need some sort of notion of concentration of measure to kick in. So like it's great on averages, it's great on medians, it's terrible on maximums. So because if you have n data points, it has one unique maxima. And you can imagine that if I'm doing bootstrap data samples, if you get that maximum point, it's going to output that. If you don't get it, it's going to be something lower. And so the maxima for some test statistics doesn't work as well. And so I think where they might not work that well is the maximum statistic, because it's very much an empirical sort of thing. But if you're basically using any statistic that concentrates to some value as n gets very large, the bootstrap will work very, very well, because the maximum statistic does not do that. The maximum is always increasing with the size of the data set. Okay. Any questions on that? You'll definitely have some practice with this on your homework.
Just a clarification thing. When we draw the samples, do we draw from the full data set, and whatever we don't use now becomes the test set?
Yeah, that's certainly one way of doing it. So this is a strategy. If you have only like 20 data points, it's just going to be really hard to say anything. And so often, but like, and with that many data points, with 20 data points, like it does make a difference whether you train on 10 and versus training on 15 when it comes to regularization sort of things. You want to use all the data you can. And the Bootstrap allows you, because you're sampling with replacement, you're going to get the same data point more than once. That's okay, because the size of the data set is still staying relatively the same. And so yeah, you'd sample the Bootstrap data set uniformly at random with replacement, and then of the points that you didn't resample, you'd use those for your test set, and you do this many times, and you get some, because that is now your test statistic. And then basically the splitting is the Bootstrap thing going on. There's more detail in the book on how to do this.
I have another question.
Mm-hmm.
Let's say I'm concerned about the average of some distribution of data that is kind of power distributed. So the average is going to be really skewed by whether I saw something in that long right tail or not. And if I take a small number of samples and then I do this bootstrapping, I'm going to increase my confidence that my average is kind of small. Like I'm going to get arbitrarily confident in that computed average. But since I never got one of these data points from that long right tail, I probably shouldn't be that confident. How do you deal with that issue?
Yeah, so this is a really, really great question. And this is similar to, so there's two sort of downsides. Some test statistics don't work very well, like the max, because the distribution of the max depends so clearly on the size of the data set that you got. The second issue that you're bringing up is, well, look, what if I have a very, very heavy tail? My function, if I only got a finite amount of data, I'm probably not going to see something in that tail, and it's not going to converge. I'm going to get some very, very overly optimistic thing. You're absolutely right. You are not sort of going away. You're not beating the central limit theorem. You're not beating the underlying statistics. What the Bootstrap gives you is basically the error in the Bootstrap estimate is going down faster than your error of estimation, the best estimator in hindsight. And what I mean by that is if you're doing empirical mean, if you're estimating empirical mean on unbounded data, so it has a heavy tail, the estimate of the mean, assuming it exists, will go down like 1 over square root of n, or like some constant over square root of n. And that constant depends on the range of your data. And so the estimate is going down like 1 over square root of n. The error in the Bootstrap estimate is going down like 1 over n. And so basically the error in the Bootstrap is going down faster than the best estimator's true error. And so what I'm saying is that like you're never going to be beating sort of these issues where the error is so large in your estimator. If you have these heavy tails, these max functions, that's unavoidable. There's some amount of unavoidable error there. Like if you have heavy tail distributions, of course, if you never see something in a heavy tail, you're never going to learn it. And I think this is actually most easily seen where like how the theory of this stuff works. It has everything to do with how quickly this function converges to this function. And so if you have in this difference here is going down like 1 over square root of n, no matter what. For any distribution, this difference is going down like 1 over square root of n. The problem that you're bringing up though, is that if you have a very, very heavy tail distribution, that means that this green function is actually super, super going like this and not hitting 1. It's very, 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 it's just going up very, very slowly. And then it's going, it's very, very far out here. And so even though this distance is very, very small, because it's such a, the x-axis is so large, you could get this large deviation. And so the bootstrap will never be able to beat this, this unavoidable fact. But basically, the error in the bootstrap is going down significantly faster than the best sort of estimator in hindsight, sort of like the true statistics of this problem. And so basically, why we like the bootstrap is you're not getting around thinking hard about, well, there is some true concentration of measure, like how quickly do random variables converge to their true distributions. And basically the bootstrap, in like you could think very, very hard about using Bernstein confidence intervals or Talleyrand's sort of stuff and do these very complicated empirical process theory, or you can just use the bootstrap because it's about as good as the most intelligent thing you could have done in hindsight if you're trying to build a confidence interval.
Okay, thanks.
Okay. So I will now hand it over to Jamie, and she will talk about unsupervised learning.
Yeah, great. All right, so let's see about this. Let's see. All right, so far this term, we've largely been talking about, we keep saying supervised learning, right? And what that means, and what we mean by that is that we have thus far been thinking about problems where we have some X, and from that we're trying to predict some Y, right? And the idea is that like the data we're initially given is labeled with both X and Y, both in terms of regression and classification. And the goal is then for future data points to be able to predict their new Y, just seeing their values for X, right? Their feature values should be enough to predict Y, either some real value or some classification decision for a new point X, right? Unsupervised learning, on the other hand, is saying we have a bunch of data in some high dimension maybe, and we'd like to learn something about its structure, and this could be useful for a bunch of different reasons, right? So we're going to start by talking about clustering, which is one particular way to look at a data set and try to understand some inherent structure it might have. Okay? So one motivating example is you might work for Google or some other large company where there's a huge amount of image data, right? You have many, many, many images. How well, you might be wanting to say something about like, here are a collection of images, and here
Is she cutting out for anyone else, or is that just me?
Yeah, she's gone now.
Oh, okay. That's suboptimal. Let's see if I can.
Yeah, she's back.
The slides.
Yeah, you're muted.
Sorry about that. Monday morning seemed to be the time when my internet is worse. I guess that's the one time during the week that everyone else is motivated to actually be doing work. Okay, So suppose you have a big collection of images and you'd like to say, these are images that are very like each other. These are images that are very like each other. And you don't actually want someone to go through and hand curate and say, these are images of seascapes, these are images of flowers, these are images of sunsets, and these are images of pastures, right? You might want some kind of way to automatically find collections of images which are like each other. Similarly, if you're, again, working for some large search engine, you might want to be able to cluster your search results into different categories. So if you search for and oddly enough, this was not my slide. If you search for something such as the English word race has several different meanings within the English language. And it would be natural when someone searches for a term that has lots of ambiguity or has many different meanings to categorize the search results that you found into different categories corresponding to something like those different meanings. And it would be nice if this categorization didn't have to happen sort of by hand for every ambiguous term someone might search for, but instead that there might be some like natural way to cluster these different kinds of search results automatically. So as we begin to get slightly more formal, and we won't really have time to talk too much about this today, we'll get there next time. Clustering can sort of be abstracted away from all of these applications as the following problem. We imagine we just have some collection of data. In this example, we maybe have data in 2 dimensions, but the dimensionality might be quite high in the case of images or something like that. Okay? And clustering simply says, okay, we have a large collection of data. Ask the person or the user or the person who's sort of looking for some segmentation of your data set into sort of pieces in which the data set is more similar, pieces in which the individual data points that belong to those pieces are more similar. Ask them how many clusters they'd like. And in this case, one natural answer might be 5, because as you can visualize in this 2-dimensional space, it looks like there are sort of 5 epicenters where data is fairly tightly concentrated. And then as a function of the number of clusters, which we usually refer to as K, that the user asks for, we'd like to pick an assignment of points to up to 5 clusters, which minimizes some objective function. Okay. So to be, just to write this in slightly more mathematical notation, you fix some number of clusters, and then you assign each point in your data set to one of K clusters, right? For some clustering algorithms, you're asked to pick centers for each of your clusters. And then your goal is just to minimize some function, right? We've been doing this all semester, quarter, all quarter. But the goal will be, rather than to pick some hypothesis to minimize loss, now we're going to be looking at assigning points to cluster to minimize some other function. Okay. So kmeans is just a particular objective function you might care about optimizing when considering some cluster. Right? And the objective function just asks, we're going to pick some centers for each of our K clusters. Right? So this is an example of a clustering objective that actually wants centers for each of the clusters. And the request or the objective function measures the amount, the average distance between every point and the center of its cluster in L2 squared distance. Okay. So, right, so this is just summing up over all points in my data set. This is just the distance to the center. Okay. All right. So you might ask how one can computationally, how one can assign points to different clusters to minimize this quantity, right? And if we had the centers fixed, beforehand, that's maybe not so challenging. On the other hand, these are also things we choose, right? We choose the centers. So how do we, computationally speaking, choose both centers and assignments of points to those clusters? And unfortunately, the short answer is we can't exactly optimize this, right? For general data sets, the problem of simultaneously picking centers and assigning points to those centers to minimize the k-means objective is NP hard. There are lots of cases, however, in which this does actually admit an exact solution in polynomial time, but we won't talk about those here. Okay? Nevertheless, there are several algorithms that work reasonably well in practice, and we'll talk about one in particular, which is sort of just a greedy heuristic, which is often used in practice, and we'll talk about that next time. Great, and we'll stick around for questions.
I have a question.
Sure.
It's about the motivation of clustering. So Kevin just discussed it like half an hour ago about the lack of locality in higher dimensions. So in higher dimensions, everything is uniformly as far from each other as they're close, and images are super high dimensional. So how does clustering, like how does the motivation for clustering work there? I can see how it works in the algorithm.
Yeah, so the short answer is yes, the curse of dimensionality may still impact you when you're thinking about an unsupervised problem in high dimensions, right? So you probably don't want to think about doing clustering on some super high dimensional data set. You might want to first apply something like dimensionality reduction, which we'll talk a little bit about on Wednesday, right? So there are often ways to represent, and Kevin alluded to this earlier, there are lots of ways to represent data that is initially represented in high dimensions in many fewer dimensions. And whether or not that works well will depend a lot upon the structure of your data. But there are many cases in which it does work well.
Okay, thank you.
I had a really quick question just about the homework. Are you guys expecting code solutions as well as the graphs for, I mean, obviously the questions that require code?
Go ahead, Kevin. I see you unmuted yourself.
Wait, so
I think the answer is
any
yes.
Any problem that asks for a graph, you should include the code. Any code, I mean, really any code that you're writing,
Okay.
you should throw it in there.
Okay, just making sure. Thank you.
Yep. Any other questions?
I kind of wanted to ask more about the Bootstrap thing. And basically what that looks like in industry. I mean, it's really just the same question I already had. It just seems to me like if you build yourself some confidence interval around some metric based on a small number of samples, then all of the like synthetic pulls from that distribution you created for yourself are really correlated to one another because they're from just your original single sample. So I don't understand the intuition for why you would become more and more confident there. I get why you can like get a number and why that might be meaningful, but if someone came to me and said like, I'm 95% certain of this mean based on my 20 point.
No, that's not how you would say it. You would say that we computed 95% confidence, bootstrap confidence intervals.
Okay, so you
don't say that like 90% of the time, like it's going to be this value. You very much say that these are 95% bootstrap confidence intervals. And so everyone knows that like you should take these with a grain of salt.
Okay.
but like they are. When you start computing these things, you'll find that they're way more efficient. They're way more sample efficient than you think they might be. And so because the problem is that if you just compute and say mean and variance of some estimate, that's pretty good if you can do that. But like if you just want to have like the function estimate and plus or minus some uncertainty, there's really not many ways to do that. And the Boostrap is one way to give you the ability to put some sort of amount of uncertainty on it. But your thinking is correct in that like you can most of the time think of these Boostrap confidence intervals as almost a lower bound on uncertainty. And so like anything you get out, it's gonna like the truth is probably actually even more uncertain than that. So if you give me an estimate that's 0.75 with plus or minus 0.25, like your estimate's garbage. I mean, I don't, and that's really how they're used a lot in practice, where it's like everyone knows that these things are not sort of like to be totally trusted blindly, but it's some signal about what the variation we should expect in this, and even just that is it's part of the conversation to allow you to basically follow up with more studies. You're like, well, what do can we get that uncertainty down? Do you think it's the lack of data? Do you think it's the model error? What can we do? And so that's how these Boostrap confidences are used so much in industry, where it's basically it's part of the conversation. It's not the end of the conversation. It's part of the conversation of trying to quantify uncertainty, because just numbers in a table is pretty misleading on its own.
Yeah, and we can we can talk more about like what confidence intervals would mean, how certain we are about this, how much we actually think this might vary if we actually could draw a fresh data set. But we haven't, other than Hufting's inequality, we really haven't introduced the tools to do that in this course. There are ways to do it, but they generally involve thinking more about probability.
Really. Okay, thanks.
Yeah.
Hi, I have one question. So usually for the single cell iron-seq data analysis, so it's a very big matrix. Each row is one gene and each column is one single cell. So usually people, they want to know the similarity or the distance for each two cells. So usually what they do is they run the PCA on all the genes. Like usually human have like 30,000 genes, and they run a PCA and get like a top 30 or 50 PCA, and then they run like UMAP or t-SNE. Then they, in the UMAP space, they try to find the distance of two cells. Do you think this is a good way, or do you have some other comments on this approach?
Yeah, I can speak to a little bit to that. So I won't go too deep because Jamie's going to talk about, we haven't talked about PCA yet, and that's what Jamie's going to talk about on Wednesday. But just as a quick answer, so yes, this is getting to what Jamie was mentioning a second ago about how you want to do some amount of dimensionality reduction first before doing nearest neighbors or similarity sort of computations, because otherwise you're getting spurious sort of errors. And doing PCA at least is assuming that your data lives on a linear manifold and then projecting it down to a low dimensional space, which is a very reasonable thing to do. So PCA is very reasonable if you believe your data lives on a linear manifold. The second step of that procedure, which is very common to use UMAP or t-SNE in particular, that I would urge extreme caution in looking at those plots. It's become extremely popular in single cell RNA-seq to be showing plots of t-SNE things and different clusters of data. But like, it's also, you know, in these clusters, you're like, oh, that cluster's all this cell type, and this cluster's all that cell type. Well, the truth of the matter is that if you put random data into Disney that's not clustered at all, you will get clusters out.
Yes.
And it's just looking at noise. And this is one major problem in unsupervised learning, that it's basically very hard to benchmark, or it's very hard to give validation on, because in supervised learning, we have a test accuracy. It's just a number. Like, I don't care what you did in your model, like it either worked or it didn't, because there's a test accuracy. In unsupervised learning, sometimes you get these plots out, like, is this good? Is that bad? Well, it looks good. Is that helpful? Yeah. How helpful is it? Is it misleading? There's all these sort of questions, and this is the biggest challenge with unsupervised learning research, is like, how do you measure the value of a particular output? And this is a very hard thing to do. And typically, to actually validate one of these things strongly is to, or very rigorously, is to do user studies and things, like whatever particular domain it's being used for. But it's a challenge.
Okay. I have another question. So if I have two data side, for example, like one is a human, one is other like mouse, I want to in this data side. I assume there is has some like a conservation. So I put all the cells from human and mouse in the same like PCA space, and then I calculate the two cells, the distance. Do you think this approach makes sense? I mean, should I use a PCA distance, or should I use the app to calculate the two cells?
So you're breaking up a bit. I don't know if it's just on my end. So I couldn't totally hear.
I'm sorry. Oh, I'm sorry. So I just want to know if I have this two data, if I have one data set, I want to know two cells, the similarity or distance between them. Should I on the PCA space, like the top